There is a region of the sky, in the direction of Bootis, where almost nothing exists. It is roughly 330 million light-years across, and a volume that size should hold something like 2,000 galaxies. It holds about 60. If our own galaxy sat at the middle of it, we would not have known that other galaxies existed until the 1960s. It is the emptiest large thing anybody has ever found, and it is not empty. Nothing is. Every cubic centimeter of that void is filled by a field, and that field has a value in it, the same value it holds here, the same value it holds inside every atom of every star. That value is the only reason an electron has any mass at all. Take it away, and matter comes apart. It is the floor that everything else is standing on. And the measurements we have taken say that the floor is not the bottom. There is a lower place the field could fall to, and if any part of it ever falls, the rest follows, everywhere, at nearly the speed of light. Tonight, we are going to take the end of everything apart and find out how close it actually is. By the end of this, you will understand what the true vacuum really is and what a bubble of it would do to the matter you are made of. You will understand why the universe has already run this experiment more times than you can count and survived every one of them. And you will get a straight answer to whether this is going to happen, whether it could already have happened, and whether the thing that finally kills you would give you any warning at all. The answer to that last one changed in the last 2 years, and almost nobody has noticed. If you like the kind of question that does not have a comfortable answer, a like or a subscribe helps this channel more than you would think. Now, let us begin. 60 galaxies. That is what the Bootis void contains, across 330 million light-years of space, in a volume that ought to hold something in the region of 2,000. It was found in 1981, and the first reaction was that somebody had made a mistake with the survey. They had not. The hole is real. It is not perfectly empty, and that matters, because there is a thin scattering of galaxies strung through the middle of it that suggests it may have formed from several smaller voids merging together. But the scale of the emptiness is not in dispute. If you were standing on a world in the center of that void and you looked up, you would see the stars of your own galaxy, and then, past them, nothing. No neighboring galaxies close enough to resolve, no smudges of light hanging in the dark. You would grow up believing that your galaxy was the entire universe, and you would be wrong, and you would have no way to find out until you built a telescope good enough to see across 100 million light-years of nothing. That is the closest thing to true emptiness that anyone has ever found, and it is full. Not of matter. There is almost no matter in it. It is full of fields. And I should say plainly that the Bootis void is not an oddity. It is the ordinary condition of the universe. Map the largest structures out there, and what you find is a web. Galaxies are strung along filaments, thin bright threads of matter, and the filaments meet at knots where the great clusters sit, and between the threads there is nothing. Most of the volume of the universe, something like 4/5 of it, is void. The bright material we photograph and put on the covers of books is the exception. The default state of everything is emptiness, and the Bootis void is simply the largest sample of the default that anyone has found. So when I tell you that emptiness is not empty, I am not talking about an unusual corner of the universe. I am talking about almost all of it. This is the thing that gets skipped in almost every explanation of what a vacuum is, and it is the thing the entire rest of this video depends on, so I am going to be careful with it. Empty space is not an absence. It is not a gap in the universe where the universe stops. Physics has spent a century establishing that what we call a vacuum is a substance with properties, and the most important of those properties is that certain fields have a value in it even when there is nothing else there at all. And there is more than one. The electromagnetic field is there, in the void, at 0, and it is still a field, and a photon passing through is a ripple in it. The fields of the quarks and the electrons are there, at 0, waiting. Every particle we know is a disturbance in a field that fills all of space, and where there are no particles, the field is still present, doing nothing, at rest. But one field is not at zero. The one that matters tonight is the Higgs field. The Higgs field fills every cubic centimetre of that void, and it has a value. That value is about 246 gigaelectron volts, which is a number that means nothing to you yet, so let me tell you what it does instead. An electron has mass. It has a very small mass, but it has one, and having one is the difference between existing and not. A particle with no mass travels at the speed of light and cannot be slowed down, cannot be stopped, and cannot be captured. It cannot be held in orbit around anything. It cannot be bound. If the electron had no mass, there would be no such thing as an atom, because an atom is nothing more than electrons held in place around a nucleus, and you cannot hold anything in place if it is moving at the speed of light and cannot be persuaded to do otherwise. The electron has mass because it is moving through the Higgs field. That is the whole of it. The field is there, everywhere, at that value, and the electron interacts with it as it goes, and that interaction is what we experience as mass. And it is not only the electron, the W and the Z, the two heavy particles that carry the weak nuclear force, get their enormous masses from the same field, and that has a consequence you can see from here. The weak force is weak, and its range is tiny, precisely because the particles carrying it are so heavy. That is why the reaction that turns hydrogen into helium in the core of a star is so slow. Two protons have to meet, and one of them has to convert into a neutron, and that conversion runs on the weak force, and the weak force almost never obliges. In the core of the Sun, a given proton waits, on average, something like 1 billion years for that to happen. That is the bottleneck. That is why the Sun burns for 10 billion years instead of detonating in an afternoon. Take away the Higgs field, and the W and the Z go massless. The weak force becomes long-ranged and strong, and stars do not work the way stars work. The slow, patient, billion-year burn of every star you have ever seen exists because a field in empty space has a particular value. Turn the field off, and the electron goes to zero. Atoms stop being possible. Chemistry stops being possible. Molecules, stars with stable burning cores, planets, all of it stops being possible. And it does not stop over billions of years, it stops immediately, because the thing that was holding matter together was never a force between the pieces, it was a property of the space they were sitting in. Now, I want to be precise here, because this gets exaggerated constantly, and precision is the point of this channel. The Higgs field is not where most of your mass comes from. Most of the mass of a proton is not the mass of the 3 quarks inside it. It is the energy of the strong force holding them together, boiling away in there, and by the relationship between energy and mass, that energy weighs something. Take the Higgs field away, and a proton would still have most of its mass. What you would lose is the electron, and the fine structure of matter, and everything that depends on electrons being able to sit still somewhere, which is everything you have ever touched, seen, or been. There is one more thing about that field that you should know, because it explains why it is different from every other field in physics. Every other field we know sits at zero when nothing is happening. The electromagnetic field, left alone, is zero. The electron field, left alone, is zero. They have no preferred value, and empty space means the field is not doing anything. The Higgs field is the exception. It is a scalar field, which means it has a value at every point but no direction, and its energy landscape is shaped so that zero is not the cheapest place for it to be. Sitting at zero actually costs it energy, so it does not sit at zero. It rolled off that peak and settled somewhere else, and it has been sitting there at a value it cannot be talked out of everywhere in the universe since the first trillionth of a second. And in that first trillionth of a second, the field really was at zero. The early universe was so hot that the shape of the landscape was different, and the field sat at zero, and the electron had no mass, and there was no such thing as an atom anywhere. Then the universe cooled, the landscape changed shape, and the field fell into the hollow. That event is called the electro-weak transition, and everything that has ever been made of matter has been made of matter since then because of it. So that is what is filling the Booty's void, not nothing. A field, holding a value, and that value is why there is such a thing as an atom. And the vacuum has structure even beyond that. It is not still. Quantum mechanics does not permit any field to sit at a perfectly fixed value with perfect certainty, which means that even in the deepest emptiness the fields are jittering. Particles are appearing in pairs and annihilating each other before anything can notice, and the whole thing is seething. This is not speculation. It has been measured in the tiny attractive force between two uncharged plates held a fraction of a micron apart, a force produced by nothing except the fluctuations of empty space itself. So the Booty's void is not a hole in the universe, it is a region where the matter has been removed and everything else has not. And here is where the trouble starts. That value is not arbitrary. The field is not simply sitting at some number that somebody chose. It is sitting where it is because that is a low point in its own energy landscape. Every field has a potential, a shape that describes how much energy it costs for the field to have a particular value, and the field falls to wherever that cost is lowest and stays there. The Higgs field found a low point about a trillionth of a second after the beginning of the universe, settled into it, and has been sitting there ever since. It is sitting in a hollow. That is the word I am going to use for the rest of this video, and I am using it because it is what the mathematics actually describes. A hollow, a dip in the landscape, a place where the field is lower than it is on either side and therefore has no reason to move. But a hollow is not the same thing as the bottom. You can be sitting in a dip halfway up a hillside. Everything around you slopes upward, and if you look only at your immediate surroundings, you would swear you are at the lowest place there is. And then you walk over the rim, and the ground drops away for 1,000 meters, and you understand that the place you had been resting in was never the bottom of anything. It was a shelf. The question this whole video is about is whether the Higgs field is sitting in the bottom of the universe or on a shelf. And there is a real answer, and we can calculate it, and the answer is not the one anybody wants. Now, the honest admission before we go on, because I owe you one in every section, and this one is a real limitation on everything I am about to say. We have never measured the Higgs field anywhere except here. We have never sent an instrument to the Booty's void, and we never will. What we have is light. Light from galaxies 100 million light years away, and 1 billion, and 13 billion, and every one of those galaxies is made of atoms, and every one of those atoms produces light at exactly the wavelengths that atoms here produce light at, shifted by the expansion of the universe and by nothing else. The spectra match, the chemistry matches. The physics of the most distant galaxy we have ever resolved looks identical to the physics in the space around us. That is strong evidence that the Higgs field has the same value everywhere in the observable universe. It is not the same thing as having gone there and measured it. Every claim in the rest of this video rests on that inference, and I would rather you knew that than found out later. So, empty space has a value in it. That value is why you exist. What decides what the value is, and is the one we got the lowest one available? The answer comes down to two numbers, and they were both measured in the last 15 years, and together they say something that a lot of physicists would rather they did not. 125 giga-electron volts and 173. Those are the two numbers. The first is the mass of the Higgs boson. The second is the mass of the top quark, the heaviest particle in the Standard Model, a thing so heavy it decays before it can even form the bound states that every other quark forms. Between them, those two numbers decide the shape of the Higgs potential, and the shape of the Higgs potential decides whether the hollow we are sitting in is the bottom of everything or a shelf on the side of a cliff. They say it is a shelf. Here is how, in plain terms, because this is the technical heart of the video, and I am not going to leave it sitting there in jargon. The Higgs field interacts with itself. How strongly it does that is described by a single number, and that number is not fixed. It changes depending on the energy you probe it at. This is not a trick or an approximation. It is one of the best tested features of the theory, and the same thing happens to every force we know. Look at the strong force at low energy, and it is overwhelming. Look at it at high energy, and it fades. The numbers run. The Higgs self-interaction runs too, and what drags it around more than anything else is the top quark. The top quark is so heavy that it couples to the Higgs field harder than anything else in the universe, and its effect is to push that self-interaction number down as you go to higher energies, down and down, and if you follow it far enough through the ordinary energies of a collider, past the energies of a cosmic ray, up and up, then somewhere around 10 to the 10th giga-electron-volts, which is roughly 100 million times the energy at which the Higgs boson itself was found, the number crosses zero and goes negative. And when it goes negative, the shape of the potential turns over. That is the whole argument. Beyond that energy, the landscape stops sloping up and starts sloping down. There is a deeper place for the field to be. There is a true vacuum, at a field value astronomically higher than the one we live in, and the energy of that state is lower than the energy of ours. We are on the shelf. The ground beyond the rim does drop away. And I want to be precise about scale here, because the numbers are easy to say and hard to hold. The energy at which the potential turns over, around 10 to the 10th giga-electron-volts, is about 100 million times higher than the energy at which the Higgs boson itself lives. And the highest energy in physics, the Planck scale, where gravity becomes as strong as everything else and where our theories stop working entirely, is around 10 to the 19th. So the instability sits in a strange middle place. It is far above anything we can reach, far above anything a star can reach, and still far below the point where the equations break down. Which means we are extrapolating. We are taking a theory that has been tested up to about 10,000 giga-electron-volts and running it 100 million times beyond that, and asking what shape it makes out there. Everybody involved knows this. If there is anything at all in the gap, any particle, any interaction, anything we have not found, the shape changes and the answer changes with it. That is not a reason to dismiss it. It is a reason to hold it carefully. The metastability of the vacuum is not a measurement. It is a consequence of taking our best theory seriously in a place where we cannot check it. So the obvious question, the one you should be asking, is what stops the field from going there right now? A wall. Between our hollow and the true minimum, the potential goes up before it comes down, and that hump is a barrier. Classically, that is the end of the story. A ball resting in a dip does not spontaneously roll over a hill that is higher than the dip. It has no way to get the energy. Quantum mechanics does not respect that. In quantum field theory, a field sitting behind a barrier has a small probability of appearing on the far side of it without ever passing through it. Not going over, through, tunneling, in the same sense that a radioactive nucleus tunnels when it decays. And the way it happens in a field that fills all of space is not that the whole field jumps at once, which would take infinite energy. It happens in one place, a single region, somewhere, of a certain critical size, spontaneously finds itself in the true vacuum, a bubble. And the shape of the object that does the tunneling has a name and a beautiful description. It is called the bounce, and it is the mathematical solution that describes the field making the transition, and it tells you both the probability of the event and the size of the bubble that results. The whole framework was built in the 1970s, and it has not needed to be revised. And the calculation of how likely that is, and how big such a bubble has to be, and what happens next, was worked out in the 1970s, and is one of the cleanest pieces of theoretical physics ever done. And there is a detail in that calculation that I find genuinely unnerving, so I am going to give it to you. The bubble has to reach a critical size. A region of true vacuum that appears too small does not survive because the surface of a small bubble costs more energy than the interior saves, and it collapses back to nothing before it goes anywhere. Only a bubble that appears already larger than a certain radius is stable, and once it passes that radius, the energy released by the interior beats the cost of the surface and the bubble grows without limit. So the tunneling does not produce a slowly widening patch of new physics. Nothing gradual happens. Either a region of true vacuum appears at or beyond the critical size, in which case it is immediately unstoppable, or it appears smaller, in which case it vanishes and nothing at all has occurred. There is no partial version of this event. There is no early stage. It goes from nothing to inevitable in a single step, and the step is instantaneous. So how likely is it? The lifetime of our vacuum, calculated from the standard model as it stands, comes out at roughly 10 to the power of 526 years. And I want to make sure the shape of the claim is clear before I give you the number, because it is easy to hear metastable and hear doomed. Metastable does not mean fragile. It means there is a lower state available and a barrier in the way. A block of diamond is metastable. Graphite is the lower energy form of carbon, and every diamond in existence is slowly, imperceptibly, on a timescale far longer than the age of the universe, trying to become graphite. Nobody worries about it. The barrier is enough. The question with the vacuum is exactly the same question, and the entire argument is about how high the barrier is. Stop, because I have watched people skate over that number, and I do not want you to. That is not 526 years. That is not even 526 billion years. 10 to the power of 526 is the number you get by writing a 1 and then writing 526 zeros after it. If you wrote 1 0 every second, it would take you nearly 9 minutes just to write the number down. The universe is 13.8 billion years old. Written the same way, that is a 1 followed by 10 zeros. 10 zeros against 526. The oldest light in existence, the microwave background, has been travelling since the universe was about 380,000 years old, and it is still arriving from every direction at a temperature of 2.7 degrees above absolute zero. That light is the closest thing to a direct look at the early universe that we will ever have, and when you look at it, you are looking at a universe in which the Higgs field had already settled into exactly the hollow it is in now. It got there in the first trillionth of a second. It has not moved since. 13.8 billion years of stars forming and dying, galaxies colliding, black holes swallowing everything within reach, and the field has not so much as twitched. And on the time scale of that lifetime number, all of that is the first instant. The entire history of the universe, everything that has ever happened, does not register as a fraction of the time we are talking about. It rounds to zero. So why is anyone worried at all? 2 reasons, and I am going to give you both, and the second one is the one that actually matters. And before that, a word about what that lifetime figure actually is, because it is not a prediction of when this will happen. It is a half-life in the same sense that a radioactive atom has a half-life. It does not mean the vacuum is safe for 10 to the 526 years and then decays. It means the probability of decay in any given stretch of time is a constant, and that the probability is so tiny that you would have to wait that long for it to become likely. The vacuum could decay tonight. That is not a rhetorical flourish, it is what the mathematics permits. A quantum tunneling event has no schedule and no memory, and the fact that it has not happened in 13.8 billion years does not make it less likely to happen in the next second than it was in the last one. What the number tells you is how small the chance is. And it is so small that if you had been running the experiment since the beginning of the universe, in every cubic meter of the observable universe, all at once, you would still be waiting. The first is that the number is fragile. That lifetime is extraordinarily sensitive to the top quark mass, and the top quark mass is genuinely hard to pin down. The measurement itself is careful. The difficulty is that the quantity a collider measures and the quantity the equations need are subtly different things, and translating between them is a real theoretical problem that people argue about. Move the top quark mass by 1 or 2 giga-electron volts, which is well within the honest uncertainty, and the answer moves. In one direction, the vacuum becomes absolutely stable, and there is no deeper minimum at all, and this entire video is about nothing. In the other direction, the lifetime collapses by hundreds of orders of magnitude. We are sitting almost exactly on the boundary, 2 to 3 standard deviations from absolute stability, depending on whose treatment of the top mass you trust. And nobody knows why. I am going to come back to that at the end, because I think it is the most interesting thing in this entire subject, and it has almost nothing to do with doom. The second reason is that everything I have just told you is the spontaneous rate. It is the rate at which the field tunnels through the barrier by itself, in empty space, with nothing helping it. There are things out there that could help it. There is one mechanism that could do that. It is the only version of this that anybody who actually works on the problem loses sleep over, and I will get to it. But first, you should know what you are being threatened with, because the honest answer to what a bubble of true vacuum would do to you is not what you think, and it is not an explosion. A neutron star is what happens when a star runs out of fuel and its core collapses so violently that electrons and protons are crushed together into neutrons. Its surface gravity is 100 billion times what you feel standing on this planet. Some of them carry magnetic fields 1 trillion times stronger than the sun's, strong enough that at 1,000 kilometers away, the field alone would tear the electron shells of your atoms into unrecognizable shapes. It is the most stubborn matter in the universe, and against a true vacuum bubble, it offers exactly as much resistance as air. Here is what the wall of that bubble actually does. Inside it, the Higgs field is not at the value it has out here. It is at the true minimum, which is a value enormously larger. Every particle whose mass comes from the Higgs field, therefore, has a different mass in there. The electron does not weigh what it weighs out here. The quarks do not weigh what they weigh out here. And the delicate arrangement that lets a proton exist and lets an electron sit in a bound orbit around a nucleus and lets a nucleus hold together at all against the mutual repulsion of its own protons is not an arrangement that survives having its input numbers changed by many orders of magnitude. So the atoms in that neutron star do not get blown apart, they stop having a reason to exist. The structure that made them possible is withdrawn, and what is left is not debris, it is a region in which the question of what an atom would be does not have an answer. And it goes deeper than the electron, because the quarks get their masses from the same field, and the nuclei of every atom in the universe are held together by a balance that is exquisitely sensitive to those masses. The proton is 2 up quarks and a down. The neutron is 2 downs and an up. The neutron is slightly heavier, by about 1 part in 1,000, and that tiny difference is the reason a free neutron decays in about 15 minutes and a free proton does not. And it is the reason hydrogen exists at all, rather than everything having collapsed into neutrons in the first minutes of the universe. That difference in mass comes from the quark masses, which come from the Higgs field. Nudge those numbers, and the simplest nucleus after hydrogen, a proton and a neutron stuck together, stops being bound. If that link fails, the first step of the reaction that powers every star in the universe fails with it, and there is no fusion anywhere, and no star ever lights. So the Higgs field is not merely holding electrons in orbit, it is setting the terms on which nuclei are allowed to hold together, and therefore the terms on which stars are allowed to burn. Every point of light you have ever seen in the sky is downstream of a number that lives in empty space. That is the distinction I want you to hold, because it is what makes this different from every other catastrophe this channel has ever covered. A supernova destroys matter by doing something violent to it. A black hole destroys matter by pulling it somewhere it cannot come back from. A true vacuum bubble does not act on matter at all. It changes the rules that matter was obeying, and matter simply stops. Density is not a defense. Distance is not a defense. Being inside the core of a neutron star is not a defense. There is nothing you could build, no material you could hide behind, no depth you could go to. because the thing being altered is not the material, it is the space the material is sitting in. And there is a second object that makes this even sharper, and it is what a star like the Sun eventually becomes. A white dwarf is the exposed core of a dead star. It is about the size of a small planet, and it holds something like half the mass of the Sun, and there is no fusion in it, and no heat source of any kind. It should collapse under its own gravity. It does not, and the reason it does not is one of the strangest facts in physics. Electrons cannot be squeezed into the same state. When you compress matter hard enough, the electrons are forced into higher and higher energies simply because there is nowhere else for them to go, and the pressure that results holds the star up against its own weight. That pressure is called electron degeneracy pressure, and it has nothing to do with heat, and it does not go away when the star cools. And the strength of that pressure depends directly on the mass of the electron, which is set by the Higgs field. So a white dwarf is not merely a thing that would be affected by vacuum decay. A white dwarf is a structure whose entire existence is a direct consequence of the value the Higgs field happens to have in the space around it. Change that value and the electron degeneracy pressure changes, and the object holding up half the mass of a star against gravity is no longer holding anything up. There are billions of white dwarfs in this galaxy alone, the cooling corpses of stars that died before the Sun was born, and every one of them is being propped up by a number that lives in the vacuum. Now the wall itself. The wall is the surface where the two states meet, and it is thin. The energy inside the bubble is lower than the energy outside it, and that difference in energy is what drives the wall outward in exactly the same way that the pressure difference across a soap film drives it. The bigger the bubble gets, the more energy is released, and that energy goes straight into accelerating the wall. Which means the wall does not travel at a fixed speed, it accelerates. And because there is essentially nothing to slow it down in open space, it accelerates until it is moving at very nearly the speed of light, and it gets there fast. Within microseconds of nucleation, the wall is doing better than 99% of light speed and still climbing. And it is worth being clear about how much energy is in that wall, because it explains why nothing stops it. The wall is thin. The transition from our vacuum to the true one happens across a distance that is smaller than an atomic nucleus. And across that tiny distance sits the entire energy difference between two states of the universe, which is a quantity so large that the wall carries more energy per square meter of its surface than anything else in physics. So when the wall meets a star, the star does not slow it down in any way that matters. When it meets a galaxy, 100 billion stars, a supermassive black hole at the center weighing millions of suns, the whole structure is crossed in 100,000 years, and the wall does not notice. There is no object anywhere, at any density, of any size, that carries enough energy to push back against it. There is a number attached to this that I find hard to hold in my head. A bubble nucleating anywhere in this solar system would cross the entire solar system, from the Sun out past the orbit of Neptune, in about 4 hours. It would cross the distance to Proxima Centauri in 4 years and 3 months, which is the same time it takes light. It would cross the Milky Way in 100,000 years, and it would keep going, forever, expanding into a universe that has no mechanism anywhere in it for stopping the thing. And there is one more consequence of the wall's speed that I have not seen stated anywhere, and that follows directly from everything above. The bubble does not sweep matter up in front of it. It cannot. Anything it touches ceases to be the kind of thing that can be pushed. There is no shockwave running ahead of it, made of the debris of what it has already crossed, because the debris does not exist. Everything the wall passes over simply stops being in place, and the wall keeps going. So there is no visible front, no glowing shell of destroyed matter, no luminous edge advancing across the sky. From outside, if you could somehow watch a bubble crossing a galaxy, what you would see is the galaxy continuing to shine, because the light already in transit keeps traveling, and then the light running out all at once in a boundary sweeping across the sky at the speed of the light itself. You would not see the wall arrive. You would see the universe stop sending you light, starting from one point and spreading. And that is where the famous claim comes from, the one on every thumbnail and in every comment section, the one that says you would never see it coming. I need to take that claim apart properly, because in the form it is usually stated it is true, and then in the last 2 years it has stopped being true, and almost nobody has noticed. Before I do, the honest admission for this section, and it is a big one. Nobody actually knows what the inside of the bubble is like, not in detail. The standard model tells us there is a deeper minimum out there, and it tells us roughly where, but the physics at those field values is physics we have never tested and cannot test. Whatever new particles exist, whatever new forces exist, whatever the true vacuum actually looks like when you are standing in it, is beyond anything we can currently calculate with confidence. Anybody who tells you exactly what the interior of a true vacuum bubble is like is making it up. What can be said with confidence is the negative statement. Whatever is in there, our kind of matter is not. And there is one thing about the interior we can say with more confidence than the rest, and it is worse than anything I have told you so far, and I am saving it because it changes what the word reset means. For now, the question everybody actually wants answered: would you see it coming? Proxima Centauri could already be gone. It sits 4.24 light years away, a small red star, the closest one to ours. The light arriving from it tonight left it 4 years and 3 months ago. If a bubble of true vacuum had swept through that system 4 years ago, the star would have ceased to be a star, and the light already in transit would keep coming, and we would keep seeing it shine exactly as it always has for 4 more years until the light ran out and the wall arrived in the same instant. That is not a thought experiment. That is a straightforward consequence of the fact that the wall travels at essentially the speed of light, and so does the news. Everything you have ever known about anything outside this planet arrived as light, or as particles moving at very close to the speed of light. There is no other channel, there is no faster signal, there is nothing that outruns light, and there never will be, and every telescope ever built, every neutrino detector buried under a kilometre of ice, every gravitational wave observatory is a device for catching things that travel at that one speed. A bubble wall moving at essentially that same speed is not something you detect in advance. It is riding in the same channel as its own announcement. The photon that would tell you it is coming and the wall itself are travelling side by side, and they arrive together, which means the warning and the end are not 2 events, they are 1 event. Look out into a deep field, a patch of sky the width of a grain of sand held at arm's length, exposed for days, until the faint smudges resolve into galaxies. Some of the ones we can see now are being seen as they were within a few 100 million years of the beginning of everything. Their light has been travelling for over 13 billion years to reach us. Every one of those galaxies is a report from the past. Not one of them tells you anything about now. The most distant object we can resolve might have been swallowed by a bubble 10 billion years ago, and we would be watching its light arrive cheerfully for another 10 billion years, learning nothing. And this is not a limitation of our instruments. No better telescope fixes it, because the limit has nothing to do with the equipment. It is the structure of the universe. Light is the fastest thing there is, and every piece of information about anything anywhere has to travel at that speed or slower, which means that the further away something is, the further into the past you are necessarily looking. There is no exception and no workaround. The sun you see is 8 minutes old. Jupiter is somewhere between half an hour and an hour old. Neptune is 4 hours old. The nearest star is 4 years old. The center of this galaxy is 26,000 years old, and the light arriving from it left before anybody had domesticated an animal. The observable universe is a sphere about 46.5 billion light years in radius, and every point in it that we see as it was. There is no such thing as a snapshot of the universe as it is right now. The idea does not even mean anything. The only version of now that any observer has access to is the point they are standing on. And light is not the only thing bound by this rule. Everything is. Gravitational waves, the ripples in the geometry of space itself that we detect when black holes collide, travel at exactly the speed of light. We have measured that. In 2017, a pair of neutron stars merged 130 million light-years away, and the gravitational waves and the light from that collision arrived within about 2 seconds of each other after 130 million years of travel. That is agreement to about 1 part in a million billion. So there is no back channel. There is no faster messenger that could be pressed into service as an early warning. The universe has exactly one speed limit, and every kind of information obeys it. And this is the reason there is no possible early warning system of the ordinary kind. Every detector we have ever built, on the ground, under mountains, in orbit, at the bottom of the ocean, in a kilometre of ice at the South Pole, works by catching something that has travelled to us. If the thing that would kill us travels at the same speed as the things that carry information about it, then no arrangement of detectors, however clever, however large, however well funded, changes the outcome by a single second. You cannot build your way out of a light speed problem. There is nowhere to put the sensor. So the popular claim, in its usual form, is correct. If a bubble is coming at essentially light speed, there is no signal that precedes it, no early warning, no alarm, no chance to do anything, and no experience of it either, because your nervous system runs on chemistry, and chemistry runs on electrons, and electrons are among the first things the wall takes away. You would not feel it. There would not be time for a nerve impulse to travel the length of your arm. The idea that you could scream, that there would be a moment of realization, is a fiction invented for the drama of it. And I want to be blunt with you about how thoroughly the physics removes even that. You would not be killed, you would be discontinued. The processes that constitute you would stop having a physical basis mid-step, and there would be no remains, because remains are made of atoms. And I want to be precise about the scream in the title, because it is not a figure of speech and the physics is worth stating exactly. A nerve impulse travels along a nerve at somewhere between 1 and 100 meters per second. Sound in air travels at about 340. Light, and the wall with it, travels at 300 million meters per second. The wall crosses the width of a human body in about 6 billionths of a second. For you to scream, a signal would have to travel from wherever the wall first touched you to your brain, be processed, and travel back out to the muscles of your chest and throat. The fastest of those steps takes milliseconds, the wall takes nanoseconds. The signal would need to be about 1,000,000 times faster than any signal your body can produce, and it would need to outrun something moving at the speed of light, which nothing can do. So you would not scream, and you would not know, and there would be no moment of realization, and the thing that ended you would never have been perceived by anything on this planet at any point. The title of this video is not an exaggeration. If anything, it undersells it. Right, so that is the version you already knew, delivered properly. Here is the part that almost nobody says out loud. That entire argument depends on one assumption. It depends on the wall arriving at us at essentially the speed of light. And the wall is not crossing an empty stage, it is ploughing through gas and plasma and radiation and everything else that fills the universe, and it interacts with all of that as it goes. In the last 2 years, several groups have gone through what that interaction actually does, and their answer is that the wall slows down. And if the wall slows down, even a little, even by a fraction of a percent, then the things it produces at its own surface can get out in front of it. Which means there might be a warning after all. I am going to come back to that and give it the space it deserves, because it is the most interesting new thing in this field, and it changes what this video is about. But first, the question that follows immediately from everything I have just said, and it is the one in the summary, and it has a real answer. If we cannot see it coming, and if the light we are looking at is all old, then how do we know it has not already started somewhere? How do we know it is not on its way right now? 16 billion light years. That is roughly where the cosmological event horizon sits, and it is the single most useful number in this entire discussion. Here is what it means. The universe is expanding, and the expansion is accelerating, which means that distant regions of space are receding from us, and the further away they are, the faster they recede. And beyond a certain distance, the space between us and them is growing faster than light can cross it. Light leaving a galaxy beyond that boundary right now will never arrive here. Not in a billion years, not in a trillion, never. The gap it has to cross grows faster than it can close, and it loses the race permanently. That boundary is the cosmological event horizon, and it sits at somewhere around 16 billion light years. Now put a bubble on the far side of it. A bubble of true vacuum nucleates somewhere out there, 20 billion light years away, and it begins expanding at essentially the speed of light in all directions. It is coming for us, and it will never, ever get here. It is a thing traveling at the speed of light toward a target that is receding faster than the speed of light, and it will chase us until the end of time and lose ground the entire way. The accelerating expansion of the universe is the only shield anybody has ever found against this, and it is a real one, and it is absolute. And there is a version of cosmology in which this is not merely likely, but continuous. If the early universe underwent a period of runaway expansion, and if that expansion never fully stopped everywhere, but only in patches, then new regions of space are still being created, endlessly, and each one settles into whatever vacuum state it happens to fall into. On that account, the universe is a foam of regions with different physics, some stable, some not, and bubbles of true vacuum are opening somewhere in it constantly. That is speculative, and I want to flag it as speculative, but it is taken seriously by serious people. And if it is right, then vacuum decay is not a rare catastrophe at all. It is what the universe does all the time, everywhere, and we are simply inside a patch it has not gotten to. So the honest answer to the question the summary asks, has it already happened, is probably yes. The observable universe is not the universe. It is the part of the universe whose light has had time to reach us in 13.8 billion years, and there is every reason to think the whole thing is much larger, possibly unimaginably larger, possibly infinite. A decay rate that is agonizingly small per unit volume becomes a certainty when you multiply it by enough volume. In a universe large enough, somewhere, at some point in the history of everything, a bubble has almost certainly nucleated. And almost all of them are irrelevant to us. Distance alone is not what saves us. The geometry of an accelerating universe has quietly walled those bubbles off from us forever. That is a strange kind of comfort, and I want to be precise about how thin it is. It only protects us from the outside. Everything within our own horizon, everything close enough that light from it could have reached us, is not walled off. If a bubble had nucleated inside that region, at any point since the beginning, expanding at nearly the speed of light, it would have swept over us already. So we can say something quite hard about our own past. No bubble has nucleated anywhere in our past light cone. That is not an assumption, it is a measurement, and the instrument is us. Every point in space and time that could have sent us a signal could also have sent us a wall. The wall would have arrived by now, or arrived first. We are still here. Therefore, in the entire volume of space, and the entire span of time from which anything could have reached us, nothing did. And there is a way of stating the same point that I find sharper. The tunneling calculation gives a probability per unit volume, per unit time. It is a tiny number, but it is not zero, and the way you get from a tiny number to an actual event is by having enough volume and enough time. Our past light cone contains an enormous amount of both. 46 billion light years in radius, 13.8 billion years deep. Every cubic meter of that, in every second of that, was an independent opportunity for the field to tunnel. And the field did not tunnel, not once, anywhere, in the entire region from which a signal could have reached us. That is not a statement about how lucky we are. It is a bound. It is a hard experimental limit on the decay rate, derived from nothing more than the fact that this conversation is happening, and it is tighter than anything a laboratory could ever produce. That is a real constraint. It covers a sphere 46 billion light-years in radius and 13.8 billion years of history, and the answer is nothing, nowhere, not once. And the horizon has another consequence that most people have never been told, and it is worth a moment because it makes the geometry real. The galaxies we can see are not all reachable. We can see out to 46.5 billion light-years, but we could only ever send a signal to things within about 16. Everything beyond that, and it is the overwhelming majority of what we can see, is already permanently beyond any influence we could ever have. Light we emit tonight will never arrive there. Light they emit tonight will never arrive here. Most of the universe we can look at is already, in the only sense that matters, gone. We are watching recordings of places we have been cut off from forever. And the same geometry that cuts us off from them, cuts them off from us. Whatever happens out there, including a bubble of true vacuum sweeping through and rewriting all of it, is an event we will never learn about. Now, the honest admission, and it is the one that quietly undoes the comfort. All of that depends on dark energy continuing to do what it is doing now. The accelerating expansion, and therefore the horizon that protects us, exists because of whatever is driving the universe apart, and nobody knows what that is. We have measured its effects extremely well. We have no idea what it is. And recent surveys, mapping millions of galaxies and the way they cluster across billions of years, have produced hints that it might not be perfectly constant, that it might be weakening, that the thing we have been treating as a fixed property of space might be changing with time. The evidence is not conclusive, and reasonable people are arguing about it right now, and I am not going to tell you it is settled, because it is not. But follow it through. If dark energy weakens, the acceleration slows. If the acceleration slows, the horizon retreats outward, and things that were permanently, geometrically, mathematically unable to reach us stop being unable to reach us. The shield is real. The shield is also provisional, and it depends on a substance nobody has identified continuing to behave the way it has behaved for the last 5 billion years. And I want to be fair about the state of that evidence, because this is a live and genuinely unresolved question, and it would be easy to overstate it in either direction. The surveys mapping the clustering of millions of galaxies across billions of years have produced results that, when combined with other data, prefer a dark energy that changes slightly over time, rather than one that is perfectly constant. That preference is at the level where physicists start paying attention and stop assuming it is noise, but it is not at the level where anybody is rewriting the textbooks. It might firm up, it might evaporate, the way many such hints have evaporated before. But the reason I bring it up is that it demonstrates something about the whole structure of this argument. The shield that protects us from most of the bubbles in the universe is not a law of nature that we understand. It is an observed behavior of a substance we cannot identify, extrapolated forward, and if that behavior changes, the protection changes with it. That is the honest position. We are not safe because of a principle. We are safe because of a measurement, and measurements can move. So here is where we actually stand. We cannot see it coming. We cannot tell whether it has begun somewhere beyond our sight. And the thing that keeps most of the universe's bubbles away from us is a property of space that we do not understand and cannot guarantee. And I want to close this section by being clear about what we have and have not established, because the two are easy to blur together. What we know is that no bubble has ever crossed our past light cone. That is solid. What we do not know is whether one is crossing space toward us right now from somewhere inside our horizon, having nucleated recently enough that it has not arrived yet. That possibility is not ruled out by anything in this section, and it cannot be, because a bubble on its way to us is by definition a thing we cannot see. So the constraint covers the past completely and the present not at all. Which leaves one question: Is there anything at all, any measurement, any observation, any piece of hard evidence that tells us how likely this actually is? There is, and it is the best measurement anybody has ever made about the stability of reality itself, and it has been running for 13.8 billion years, and you are standing inside the result of it. On the 15th of October 1991, a single subatomic particle arrived, carrying about 3 × 10 to the 20th electron volts of energy. One particle, one nucleus, or something very close to one, probably a proton, moving so close to the speed of light that if you had raced it against a photon over a distance of 30 kilometers, it would have crossed the line about 100 billionth of a second behind. It had, packed into that one particle, roughly the kinetic energy of a baseball thrown hard by a professional. That comparison gets used constantly, and I am going to use it too, because the bare number is meaningless to a human being, and the comparison is not there to soften anything. It is there to make the absurdity land. All the energy of a thrown ball, carried by something so small that 100 million of them side by side would not span the width of a single atom. In 2020, when another one arrived at over 2 × 10 to the 20th electron volts, and it was given a name, and the strange thing about it was where it came from. Trace the arrival direction back, and it points at the local void, a region of space where there is essentially nothing at all, no galaxy, no obvious source, no object anybody can identify that has any business accelerating a particle to that energy. It arrived out of a hole in the universe, and nobody can tell you what threw it. These things are not rare in the sense that matters. They are rare in the sense that a given square kilometre at the top of an atmosphere gets hit by one about once a century. But the universe is not 1 square kilometre. Particles at these energies are hitting every planet, every moon, every star, every cloud of interstellar gas, everywhere, constantly, and they have been doing it for the entire history of everything. Now here is the point, and this is the centre of gravity of this entire video. When a particle like that hits something, the collision happens at an energy that no machine we will ever build can reach. I want to be careful and precise about this, because it is usually stated wrong. The energy carried by that 1991 particle is about 40 million times the energy carried by a single proton in the largest collider we have ever built. That is a true statement, and it is the one people repeat. But a collider smashes 2 beams into each other head-on, which uses the energy far more efficiently, and a cosmic ray is hitting something that is essentially standing still. When you do the arithmetic properly, the energy actually available in a collision between one of these particles and a stationary proton comes out at around 50 times what our largest collider can produce. 50 times, not 40 million. And I would rather give you the correct number and have it be less dramatic than give you the dramatic one and be wrong. 50 times is still enormous, and that is only the collisions happening in a planet's atmosphere. Out in the places where these particles are accelerated, in the shock fronts of exploding stars, in the jets that shoot out of the centres of active galaxies at nearly the speed of light, in the magnetic fields around the most violent objects that exist, particles are colliding with other particles that are also moving at nearly the speed of light, head-on, and the available energies climb far beyond anything a planet's atmosphere ever sees. And there is something about that 2021 particle that makes it stranger still, and it is worth knowing, because it tells you how far the real universe outruns anything we can build. A particle at those energies cannot travel far. Space is filled with the microwave background, the cold leftover light from the beginning, and to a proton moving at that speed, those photons are not cold at all. They hit it like gamma rays, and every collision strips away energy. The result is a limit. A proton above roughly 5 × 10 to the 19th electron volts cannot survive a journey of more than about 150 million light years without being ground down below that threshold. Which means these particles are coming from close by, in the terms this channel usually deals in, within a couple of 100 million light years. And when you trace that particle's arrival direction back into that volume, you find the local void, emptiness, Nothing there capable of accelerating anything, let alone accelerating a single proton to the energy of a thrown baseball. Nobody knows what did it. That is not a mystery I am inventing for effect. It is an open problem, and it means the universe has a particle accelerator somewhere that we cannot see and cannot explain, and it is running at energies that make every machine we have ever built look like a toy. And the argument that follows was made in a paper published in 1983, and it is one of the most elegant arguments in physics, and it goes like this. If a high-energy collision could knock the Higgs field out of its hollow, then somewhere in our past light cone, one of them would have done it, because the collisions have already happened, not a few of them. Count up every high-energy collision that has occurred anywhere in the volume of space and span of time from which a signal could have reached us, and the number of heavy nuclear collisions alone runs to something on the order of 10 to the 47th. 10 to the 47th, a 1 with 47 zeros after it. Every single one of them, at energies far beyond anything we can manufacture, in every corner of everything we can see, over 13.8 billion years. And there is a number attached to how rare these are that I want to give you, because it is the only reason we do not see one every day. Above 10 to the 20th electron volts, the flux is roughly 1 particle per square kilometre per century. That is the whole reason we needed detectors covering thousands of square kilometres to catch them at all. And it is the reason we have only a handful of events at the very highest energies ever recorded. But the rarity is a rarity of detection, not a rarity of occurrence. The atmosphere of this planet is a target a few 100 million square kilometres across, and it is being struck continuously. Multiply that up across every planet, every moon, every star, every cloud of gas in the galaxy, and then across the 100 billion galaxies in the observable universe, and then across 13.8 billion years. The rarity vanishes. What is left is a number so large, it stops behaving like a number. And I should say what those collisions actually do, because it matters for the argument. When a particle at these energies strikes a nucleus, the collision produces a shower, thousands of secondary particles cascading downward, each one producing more, spreading out into a front that can cover many square kilometres by the time it arrives at the ground. Inside the first instant of that shower, for a fleeting moment, in a volume smaller than a nucleus, the energy density is higher than anything a machine can produce. If a concentration of energy like that could kick the Higgs field over the barrier, this is where it would happen. And it has happened everywhere, constantly, since the first stars. The universe has been hitting the reset button not once, not occasionally, continuously, everywhere, at energies we cannot match for the entire history of time. And the hollow held, every single time. That is the measurement. That is the thing I want you to take away from this video if you take away nothing else. Our existence is not a lucky escape from a danger that might arrive tomorrow. Our existence is the output of the longest and most brutal experiment ever conducted on the stability of the vacuum, and the experiment came back negative 10 to the 47th times in a row. And it is worth naming the machines that produce these particles, because the universe's accelerators dwarf anything we will ever build. When a massive star collapses and explodes, the shock front that races outward through the surrounding gas acts as an accelerator. Charged particles bounce back and forth across that front, gaining energy on every crossing for centuries. The expanding remnant of a supernova is a particle accelerator light years across, and it runs for 1,000 years without maintenance. Bigger still are the jets. At the center of an active galaxy, matter spiraling into a supermassive black hole launches 2 beams of plasma outward at nearly the speed of light, and those jets can extend for hundreds of thousands of light years, further than the galaxy that made them. The magnetic fields wound through them accelerate particles to energies that no terrestrial machine will ever approach. That is the competition. A ring of magnets a few kilometers across against a jet 100,000 light years long, powered by a black hole eating a galaxy. and it settles something that people have been frightened about for 20 years. When the largest collider on this planet was switched on, there were people who genuinely believed it might trigger this, and there were lawsuits, and there was real public fear. That fear was understandable, and it was also, in the most literal sense, already answered. Nature had run the experiment at higher energies, in greater numbers, for longer, before there was anybody here to worry about it. If a collision could do it, we would not be here to build the collider. And you might be wondering what would count as evidence that a bubble existed somewhere. The honest answer, before the work I am going to describe later, was nothing. There was no proposed observable. A bubble expanding at light speed produces no signal that can precede it, leaves no trace behind it that anyone could survive to see, and cannot be distinguished from outside, from the ordinary dark. It was a catastrophe with no observational signature of any kind, which is a strange position for a scientific claim to be in. Now, the honest admission, because I am not going to oversell this either. The argument is strong. It is not a proof. What it rules out is decay triggered by the kinds of high-energy collisions that nature actually performs. It does not rule out mechanisms that nature does not perform. It does not rule out the spontaneous tunneling I described earlier, which no experiment can ever rule out because you cannot observe a thing that has not happened yet. And it does not rule out something that operates by a completely different route, something that does not have to get over the barrier at all. The fear you walked in with was the wrong fear. It was never the colliders, it was never the cosmic rays. But the fear does not go away. It moves. There is one thing I have been holding back, and it is the only version of this that anybody who works on it actually takes seriously. It has nothing to do with colliders and nothing to do with cosmic rays, and it does not need to get over the barrier at all, because it goes underneath it. I will show you exactly what it is and how close the argument came to being proved right in about 15 minutes, and then I will tell you why we are still here. Sagittarius, a star, sits at the center of this galaxy, 26,000 light-years away, and it weighs about 4 million times what the Sun weighs. It is the largest, heaviest, most gravitationally violent single object anywhere near us. It cannot do this. It is far too big. The thing that could do it, if anything can, is a black hole with the mass of a mountain and a diameter smaller than a proton. To understand why, you have to understand the one genuinely strange thing about black holes, which is that they have a temperature, and the temperature runs backwards. A black hole radiates slowly, and the smaller it is, the hotter it radiates. A black hole the mass of the Sun has a temperature of about 60 billionths of a degree above absolute zero, which is far colder than the microwave background that fills all of space, which means it absorbs more than it emits and it grows. Sagittarius, a star, is colder still, effectively frozen at zero. Those objects are not going anywhere for an unimaginably long time. But run it the other way. Take a black hole with the mass of a large asteroid and its temperature climbs into the thousands of degrees. Take one with the mass of a mountain, compressed into something the size of a proton, and it is blazing, radiating hard, losing mass, and as it loses mass it gets hotter, and as it gets hotter it radiates faster, and the process runs away with itself until the final moments when the temperature climbs toward energies that nothing else in the universe can reach. And the rate at which they evaporate depends on their mass in a way that produces a very specific number. The smaller the hole, the hotter it is, and the hotter it is, the faster it loses mass, and the faster it loses mass, the smaller it gets. The whole process accelerates. Work through it, and you find that the time a black hole takes to evaporate completely goes as the cube of its mass, which means that a black hole with the mass of the Sun would take something like 10 to the 67th years to evaporate, which is far longer than the universe will have stars in it. But a black hole with the mass of a large mountain, around 100 billion kilograms, evaporates in about 13.8 billion years. Which is now. Which is exactly the age of the universe. So if primordial black holes of that mass formed in the early universe, They are finishing right now, in their last moments, everywhere, radiating harder and harder, climbing toward the highest temperatures anything in the universe reaches, and ending in a burst. And the final moments of one of those objects are worth stating, because they are the most extreme conditions the universe can produce without a collision. As the black hole loses mass, its temperature climbs without limit. In the last second of its existence, an object of that kind releases energy comparable to millions of tons of explosive, and in the very last instant the temperature approaches scales where our physics stops describing what is happening at all. That last instant is the closest anything in the universe comes, on its own, to the energies at which the Higgs potential turns over. Which is exactly why the black hole seeding argument had teeth. It was not proposing an exotic new mechanism. It was pointing at the one thing in the real universe that gets anywhere near the relevant scale, and asking what happens when it does. Nobody has ever seen one of those bursts. That absence is one of the strongest constraints we have on whether these objects exist at all. Those objects are called primordial black holes. They cannot form today, because there is no process now that can compress matter that hard. They could only have formed in the first instance after the beginning, when the universe was dense enough that a slight overdensity in one place could collapse directly into a black hole. Whether any actually formed is an open question. Nobody has ever found one. And the constraints on whether they exist are worth knowing, because they are a good example of how you rule something out without ever seeing it. If black holes of that mountain mass range were common, they would be finishing their evaporation now, and every one of those endings would produce a burst of gamma rays. Add up all those bursts across the observable universe, and you get a diffuse glow of gamma radiation filling the sky at a level we can measure. We have measured it. The glow is not there, so black holes in that mass range cannot be more than a tiny fraction of the matter in the universe. That does not rule them out. It limits how many there can be. And there are other mass ranges, particularly around the mass of a large asteroid, where primordial black holes are still permitted in numbers large enough that they could account for the dark matter, and where nobody has ruled them out at all. So the honest position is that these objects have never been observed, that they may not exist, that the mass range which would be dangerous is heavily constrained, and that the question is open. And in 2015, a paper argued that if they exist, they could end everything. The argument is not that the black hole smashes the Higgs field out of its hollow with brute force. It is subtler, and it is much more worrying than that. A black hole is a defect in space, a place where the geometry is bent and the ordinary rules of what a field can do are altered. And what the calculation showed is that a bubble of true vacuum can nucleate around a small black hole far more easily than it can nucleate in open space. The black hole acts as a seed. The barrier that would take longer than 10 to the 526 years to tunnel through in empty space becomes something the field can get past in a fraction of the time when there is a small black hole sitting there acting as a nucleation site. And for certain masses, the calculation showed the decay winning the race against evaporation. The black hole would seed a bubble before it managed to evaporate away. The hollow does not get climbed, it gets dug under. So, is that it? Is that the answer, that there are little black holes scattered through the universe quietly waiting to end it? No. And this is where I have to be honest with you, in a way that most videos on this subject are not, because the follow-up work went the other way, and the disagreement is live. Other groups went back through the calculation and argued that the seeded decay rate is not enhanced anything like as much as claimed, that it is suppressed by the smallness of the Higgs self-interaction, and that black holes do not in fact source rapid vacuum decay. That work was published, it is serious, and it is not obviously wrong. The field is genuinely divided. This is a real open argument between competent people, and if you go looking you will find papers on both sides published within the last 3 years. I am not dressing up a settled result as a controversy, and I am not elevating a fringe idea. The disagreement is exactly as live as I am telling you it is. And there is a second argument, and it is quieter, and it is the one I find most convincing, and it should be familiar to you by now. If primordial black holes of the dangerous mass range existed in any significant number, and if they really do seed vacuum decay as efficiently as the scary version claims, then the universe would have gone already. Those objects would have been forming and evaporating and seeding bubbles everywhere for 13.8 billion years. One bubble, anywhere in our past light cone, at any time, and this conversation does not happen. We are still here, so either those black holes are rare, or they do not seed decay, or both. Once again, our existence is doing the work that no experiment can do. And you might be wondering whether we could build one, whether some future collider could make a black hole small enough, or push the Higgs field hard enough to do this deliberately. No, and the number is not close. The energy scale at which the Higgs potential turns over is around 10 to the 10th gigaelectron volts. Our largest collider reaches about 10,000. That is a factor of roughly a million between what we can do and what would be needed. And even the most speculative designs anybody has ever sketched, machines the size of a planet, do not close a gap like that. There is no route from here to there. If the vacuum is ever going to decay, it will not be our doing. And there is a version of the black hole argument that I find more unsettling than any of the above, and it does not need primordial black holes at all. Stellar black holes form constantly when massive stars die. They are far too large and far too cold to seed anything, and the calculations agree on that. But black holes also merge, and when they do, the geometry of space in the region between them is violently distorted for a fraction of a second in ways we have now measured directly through gravitational waves. Some work has asked whether the extreme conditions during a merger could disturb the Higgs field enough to matter. The answer, so far, is no. The energies involved, enormous as they are in ordinary terms, are nowhere near the scale where the potential turns over. But it is the same question in a different suit, and every one of these routes ends in the same place. Something in the real universe gets closer to the relevant scale than we can, and the vacuum still does not budge. So the collider fear was wrong. The cosmic ray fear was wrong. The black hole route is real but contested, and our own existence argues against it. Which brings us back to the thing I promised you, and it is the newest piece of physics in this entire video. If a bubble is out there, right now, expanding toward us, is it really true that we would get nothing? No signal, no warning, no notice at all? That answer changed, and it changed recently, and I do not think most people have caught up with it. The wall is not crossing an empty stage. That is the sentence that undoes the most famous claim in this entire subject, and everything in this section follows from it. Space between the galaxies is thin, but it is not nothing. There is gas out there, roughly 1 atom per cubic meter in the deep intergalactic dark, and inside galaxies far more. There is plasma, there is radiation, the microwave background, filling every cubic centimeter of the universe with photons left over from the beginning. There is dark matter, whatever it is, outweighing ordinary matter 5 to 1, and a bubble wall expanding at nearly the speed of light is driving straight through all of it. That interaction is not free. The wall hits particles, and particles hit the wall, and every one of those interactions takes a little momentum out of it. Drag, friction. And in the last 2 years, several groups have gone through what that friction actually does to the wall, and what falls out of it is the most interesting result in this field in a decade. The wall does not accelerate forever. It reaches a terminal velocity, and that velocity is below the speed of light. Slightly below, not dramatically, but below, and that changes everything, because it means the wall is no longer riding in the same channel as its own announcement. Here is the mechanism, in plain terms. When a particle crosses the wall, it does not have the same mass on the other side. It cannot. Its mass is set by the Higgs field, and the Higgs field has a different value in there. That mismatch has to be paid for, and the way it gets paid for is by producing particles at the wall itself. Specifically, Higgs bosons in quantity radiating off the surface of the wall as it plows forward. And Higgs bosons do not last. They decay almost immediately into other things, and because the Higgs is electrically neutral, a good fraction of what comes out the far end of that decay chain is photons and neutrinos. Photons travel at the speed of light. Neutrinos travel at essentially the speed of light, and the wall does not. So they get out in front of it. A bubble expanding somewhere out there would be throwing a burst of very high energy photons and neutrinos ahead of itself continuously the entire time it expanded, and those particles would arrive here first, before the wall, ahead of the end. How far ahead depends on how much the wall is slowed, and that depends on parameters nobody has measured. For a bubble far enough away, the lead could be substantial. For one nearby, it could be nothing worth having. But the principle is now on the table, and it is a genuine reversal of the standard story. The end of everything might be preceded by a signal. And before you decide this is too exotic to take seriously, I want to point at the one case where the universe has already done exactly this. In 1987, a star exploded in a satellite galaxy of ours, about 160,000 light-years away. The core of that star collapsed, and in the collapse it produced a flood of neutrinos, and those neutrinos poured straight out through the dying star because neutrinos barely interact with anything. The light, meanwhile, had to fight its way out through the collapsing layers of the star itself, which takes time. The neutrinos arrived here about 3 hours before the light did. 3 hours of warning from a catastrophe 160,000 light-years away, delivered by particles that got out ahead of the photons. Nobody had planned for it. A handful of detectors happened to be running, and they caught a couple of dozen neutrinos, and then hours later the sky lit up, and everyone understood what those neutrinos had been. That is precedent, not proof, and the physics is completely different, but precedent. The universe has already, once, told us about a catastrophe before we could see it, using particles that outran the light of the event itself. The claim that a bubble might do the same thing is not a wild one. It is the same principle applied to a different disaster. And there is a second channel, and it reaches further. A wall being violently accelerated and shock heating everything it passes through radiates gravitational waves, ripples in the geometry of space itself, which propagate outward and, unlike light, are almost impossible to absorb or block. Those waves would be at very high frequency, and they would carry information about the wall's dynamics, and they could, in principle, be detected from cosmological distances by instruments that are being designed right now. Which means the places we already watch for the most extreme events in the universe, the collisions of neutron stars that send ripples through the geometry of space, the gamma-ray bursts that briefly outshine entire galaxies, the high-energy neutrinos that arrive from sources nobody has identified, are exactly the places where a warning would show up. We are already staring at the right part of the sky with the right instruments. We just have not been looking for this. And there is a practical problem with the gravitational wave channel that I should be straight about. The waves a bubble wall would produce sit at extremely high frequencies, far above the band that our current detectors listen to. The instruments that have already detected merging black holes are tuned to events that last a fraction of a second and ring at frequencies of tens to hundreds of cycles per second. A relativistic bubble wall radiates far higher than that. Detecting it would need instruments that do not yet exist, and some of the proposed designs for the next generation, including one intended to fly in space with arms millions of kilometers long, would cover part of the relevant range and not all of it. So this is not a warning system anybody could switch on tomorrow. It is a target, described in a paper, for hardware that has not been built. But I keep coming back to the strangeness of the situation it describes. If the calculations are right, then somewhere in the universe, right now, there could be a wall expanding at a whisker below light speed, and it could be throwing a spray of neutrinos and gamma rays out in front of itself, and those particles could be crossing space toward whatever is in their path, arriving as the last piece of information anything in that direction ever receives. Now, the honest admission, and it needs to be a serious one, because I have just told you something exciting, and I do not want you walking away thinking it is established. This is new. It is a proposal, not a finding. The papers are from the last 2 years, and the numbers in them depend on choices about the parameters of physics we have not measured and may never measure. Change the assumptions, and the signal changes by orders of magnitude or disappears. Nobody has detected anything. Nobody expects to detect anything because the prior probability of a bubble being close enough and recent enough is minuscule. What has changed is not the danger. What has changed is the story we tell about the danger, and the story was wrong. The claim that vacuum decay is the one catastrophe in physics that offers no warning whatsoever, by its very nature, in principle, is no longer something you can say with confidence. And I want to be honest about what the warning would actually be worth. Nothing in any practical sense. There is no shelter, no evacuation, no direction to run in, and no technology anybody has ever sketched that would do anything at all about a wall of true vacuum arriving at the speed of light. The bubble does not care whether you saw it. It is not aimed at you, and it cannot be negotiated with, and it will not miss. So the warning is not a warning in the sense of allowing action. It is a warning in the sense of allowing knowledge. It is the difference between an ending that happens to you and an ending you understand as it happens. And so I want to put a question to you, and I am not going to answer this one because I do not think it has an answer, and I want to know where you land. Suppose the warning arrives. Suppose the neutrinos come, and the gamma ray burst that has no source, and the gravitational wave at a frequency nothing natural produces, and suppose it is understood for what it is, a bubble, out there, coming, arriving in some number of years or months or hours that can be calculated precisely and cannot be altered by anything anybody does. And there is a strange asymmetry in the question that I keep turning over. Every other ending gives you the option of not knowing. The universe does not send a notice before an asteroid, or before a nearby supernova, or before the sun swells up. And even when it does, there is always something to be done. Preparation, evacuation, continuation. There is always an afterward in which the knowledge could have been useful. Here the knowledge is useless by construction. It cannot be acted on. It has no downstream. It exists purely as knowledge, held by things that are about to stop existing, about the fact that they are about to stop existing. Would you want to know? There is no evacuation. There is no shelter. There is nowhere to go, because the thing coming is not an object. It is a change in the rules, and it is coming for the entire universe. Knowing buys you nothing except the knowing. I think I would want to know. I think that would be the last thing our species ever figured out, and I think there would be something in that. But I am aware that is a position and not a fact, and I suspect a lot of you will disagree with me, and I would rather hear you disagree in the comments than nod along. And if it did arrive, what exactly would be on the other side of it? Because the word people use is reset, and reset implies that something comes next. The true vacuum has negative energy density, and that one fact takes the word reset away from you. Here is what it means. When you follow the Higgs potential down past the point where it turns over, it does not level off somewhere below our own value and sit there. It keeps going down, and it goes below zero. The minimum, wherever it actually is, sits at a negative energy density. In general relativity, the energy density of space determines what space does. Our universe has a small positive energy density, and that is what dark energy is, and the effect of it is to push space apart. It is why the expansion is accelerating. Positive energy density in the vacuum means the universe grows. Negative energy density does the opposite. It pulls. So the inside of a true vacuum bubble is not a fresh universe with different physics, quietly getting on with its own business under new rules. It is a region of space that is collapsing. Everything inside it is being drawn together, and the collapse is not gentle and it is not slow. a region with a strongly negative energy density crunches, and it crunches on a timescale set by the size of that energy density, and for the values the standard model suggests, that is fast. And there is a further twist here that I did not expect when I started reading about this, and it cuts the other way, so I am going to give it to you. Gravity does not simply come along for the ride in these calculations, it changes them. When you do the vacuum decay calculation properly, with general relativity included rather than bolted on afterward, gravity contributes to the energy of the bubble wall, and for some choices of the parameters, that contribution makes decay harder rather than easier. In certain regimes, gravity can suppress the decay rate substantially. In extreme cases, a false vacuum with a large enough positive energy can be prevented from decaying at all. So the same theory that says the interior of the bubble collapses catastrophically also says that gravity may be part of what has kept the field sitting in its hollow this entire time. The thing that makes the inside of the bubble a death trap may also be part of the reason the bubble has never formed. I find that genuinely difficult to hold in my head, and I do not think anybody has fully worked out what it means. Point the camera at something we can actually see doing this, because there is one. Watch matter fall into a black hole, gas spiraling inward, torn into a disk, heated by friction until it glows across the whole electromagnetic spectrum, orbiting faster and faster, the innermost material moving at a serious fraction of the speed of light. And then it crosses the horizon, and there is no more information about it, ever. Every path from inside that surface leads inward. There is no direction that is out. The geometry itself has been tipped over, so that the future of anything in there is the center. That is the closest thing in the visible universe to what the interior of a true vacuum bubble would be. And it is not an analogy I am reaching for. It is the same mathematics. A collapsing region with no exit and no future except the collapse. So the idea people carry around, the one where a bubble sweeps through and afterward the universe is still there, just running on different laws, with maybe some other kind of matter and some other kind of life eventually arising in the new physics, does not survive contact with the equations. There is no afterward. The bubble is not a reset button that returns the universe to a fresh start. It is a region that removes the conditions for matter and then folds in on itself. And I want to deal with the word reset directly, because it is in the framing of this whole subject, and it is doing damage. A reset implies a machine that goes back to a starting state and runs again. It implies a next round. When people describe vacuum decay as the universe's reset button, what they are hearing in their own heads is a fresh universe, new laws, new particles, maybe new life eventually, and a sense that something continues. Nothing in the physics supports that. The word is doing emotional work that the mathematics does not authorize. Falling out of the hollow is not falling onto a lower floor, it is falling with nothing underneath. And the collapse would not be leisurely. The timescale of a gravitational collapse is set by the density of the thing collapsing, and the energy density of the true vacuum, if the standard model extrapolation holds, is enormous. That means the interior does not take billions of years to fold in. It takes a length of time that is short compared to anything you would recognize as a duration. So the sequence, from the perspective of a region the wall has just crossed, is not a long, slow decline into a different kind of universe. The rules change, and the matter stops, and the space itself begins pulling inward, all of it inside a stretch of time, far too short for any process of any kind to occur. And that is why the honest word is not reset. The honest word is stop. There is no new physics being explored in there. There is no successor state doing anything interesting. There is a region that has stopped being able to hold anything and is now closing. And now the honest admission for this section, which is a large one, and I am not going to dress it up. All of that is standard model reasoning, and the standard model is not complete. We know it is not complete, because it does not include gravity in a full quantum treatment. It does not explain dark matter, and it does not explain dark energy. The true minimum of the potential lies at field values 100 million times beyond anything we have ever probed, in a region of physics where new particles could exist that change the entire shape of the landscape. If there is new physics between here and there almost certainly is, then the true minimum might not be where the standard model says it is, might not have the properties the standard model says it has, and might not be negative at all. This is the part of the subject where careful physicists go quiet, and I am going to go quiet with them rather than pretend to a confidence nobody has earned. The honest summary is this: according to the best theory we have, extrapolated far past the range in which we have tested it, the inside of the bubble is a collapsing region in which our kind of matter cannot exist. That is what the mathematics says. Whether the mathematics still applies out there is not something anybody can tell you. And what would it look like from outside to an observer far enough away to still be watching? That is a harder question than it sounds, and the answers in the literature are not unanimous. Some treatments find that the collapsing interior, seen from outside, behaves like a black hole forming, so that the boundary of the region becomes a horizon, and the whole thing looks, from a distance, like an enormous black hole appearing where the universe used to be. Others find the wall simply keeps expanding and swallows the observer before the interior's fate becomes relevant to them. Either way, the observer does not survive to file a report. The question of what it looks like from outside has no observer to ask it, which is a strange kind of closure and not a satisfying one. So where does this actually sit? You have now heard that the universe is metastable, that a bubble would erase everything, that it might already have happened somewhere, that we probably could not stop it and might not even see it coming. The obvious question is whether you should be worried. And the only honest way to answer that is to put it in the queue alongside everything else that is going to kill you and see where it lands. In about 1 billion years, the sun will be bright enough to end liquid water on the surface of this planet, and there is nothing anybody can do about it. That is not a speculation. The sun has been getting brighter since it formed, by about 10% every billion years, because as it fuses hydrogen into helium, its core grows denser and hotter and burns harder. Run that forward, and there is a point where the energy arriving here is enough to drive a runaway greenhouse, and the water goes into the air, and then it goes into space, and the surface goes dry. That happens with roughly 1 billion years on the clock, which means that life on this world has already used up something like 4/5 of its total allotment of time. In about 5 billion years, the sun exhausts the hydrogen in its core, and the core contracts, and the outer layers swell outward, and it becomes a red giant. It will grow until it is hundreds of times its current diameter. Mercury goes first, swallowed entirely. Venus follows. This planet is either engulfed or left as a scorched, airless, sterilized rock orbiting a monster. And then the sun sheds its outer layers into space, and what is left of the core sits there as a white dwarf, about the size of a small planet, holding half the mass of the sun, cooling slowly, glowing white, and then yellow, and then red, and then nothing at all. Keep going. In about 100 trillion years, the last stars burn out, not our sun, which is long gone by then, but the small red dwarfs, which burn so slowly and so miserly that some of them will still be going 100 times longer than the current age of the universe. When the last of them dies, star formation is over, because there is no gas left to make new ones, and the sky goes dark and stays dark. Whatever is left in the universe at that point is white dwarfs cooling toward absolute zero, neutron stars cooling toward absolute zero, and black holes. And somewhere in that long dark, if the physics allows it, the matter itself may come apart. Some theories predict that the proton, the particle that everything you are made of is built from, is not permanently stable, and that it eventually decays into lighter things. We have looked for that hard. Enormous tanks of water watched for years, waiting for a single proton out of an unimaginable number to fall apart. Nothing has been seen, which puts a lower limit on the proton lifetime of something beyond 10 to the 34th years. If protons do decay, then somewhere out around 10 to the 40th years, every white dwarf and every neutron star in the universe quietly evaporates from the inside as the matter making them up stops existing, and the era of matter ends entirely, leaving only radiation and black holes. If they do not, those cold dead stars sit there in the dark, doing nothing, for an unimaginably longer time, waiting for the black holes to finish. Either way, keep going. Keep going. Somewhere around 10 to the 100th years, the black holes finish evaporating. Even the largest of them, the ones weighing tens of billions of suns, radiate away their mass eventually and disappear in a final burst. After that, there is nothing but a cold, thin, endlessly expanding fog of photons and stray particles drifting apart forever, with no structure of any kind and no possibility of any. That is the heat death. That is the end of everything that can meaningfully be called an event. And it happens at 10 to the 100th years. The vacuum lifetime is 10 to the 526. I want you to sit with the size of that gap, because it is the answer to the question you clicked on this video to ask. The heat death of the universe, the point at which the last black hole evaporates and there is nothing left anywhere, arrives 426 orders of magnitude before the vacuum is expected to decay. Not 426 times sooner, 426 factors of 10 sooner. Compared to the timescale of vacuum decay, the entire history of the universe, from the beginning through the death of the last star to the final evaporation of the last black hole, happens in a single instant, all at once, at the very start. And there is one more way to say it that I think lands hardest. If you compress the entire expected lifetime of the vacuum into a single year, then the whole history of the universe so far, every star that has ever formed, every galaxy, every world, would occupy less than the first instant of the first second of the first day. And so would the heat death, and so would the evaporation of the last black hole. Everything, all of it, before the clock had visibly moved. Vacuum decay is not the next thing on the list. It is not on the list. Every other ending in physics happens first, by a margin so enormous that they might as well all be simultaneous. And there is a version of this list that is worth stating plainly, because it puts the whole subject in proportion. If you are looking for the thing that will end life on this planet, it is the sun, and the time scale is 1 billion years, and it is not in dispute, and there is no mechanism by which it can be avoided from here. If you are looking for the thing that ends the possibility of new stars, it is the exhaustion of gas, and the time scale is 100 trillion years. If you are looking for the thing that ends structure, it is black hole evaporation, and the time scale is 10 to the 100th years. If you are looking for vacuum decay, you are looking 426 orders of magnitude past the last item on that list, at an event that the universe as we understand it will not survive long enough to experience. So, should you be worried? No, not about this. And I am not saying that to comfort you. I am saying it because it is what the numbers say, and I would tell you if they said otherwise. The honest admission, and it is the one thing that keeps the question alive at all, that ranking assumes the spontaneous rate is the real rate. If black hole seeding works the way the scary version claims, the number is smaller, possibly enormously smaller, and nobody can currently tell you by how much because the disagreement in the literature has not been resolved. That is the one crack. It is a real one. It is also, as I said, an argument that our own continued existence pushes hard against. And one more thing about that first item on the list, because it is the one that actually applies to anything alive. The biosphere of this planet is roughly 4 billion years old, and it has about 1 billion years left before the sun's brightening ends it. That is not a prediction with much uncertainty in it. The sun is doing what every star of its kind does, and it cannot be talked out of it. So if you want a real deadline, that is the real deadline, and everything alive here is well into the back half of its allotted time. It is a strange thing to sit alongside a number like 10 to the 526. The end of everything is unimaginably distant. The end of us is not. So why does this idea have such a grip on people? Here is my answer, and it is a position rather than a fact, so take it as one. It is not the probability. Nobody is genuinely running the numbers and getting frightened. It is the completeness. Every other ending we know leaves something behind. The sun swelling up leaves the outer solar system and the sun's own corpse and whatever we managed to send away before it happened. The last star burning out leaves the black holes. The last black hole evaporating still leaves the photons, still leaves space, still leaves the laws that make photons and space possible. Every catastrophe in physics is a catastrophe for something, and it happens against a background that continues. Vacuum decay takes the background, it takes the rules. There is no place it does not reach, and nothing it does not reach into, and it does not leave a universe in which the event could be remembered, because there is nothing left that could do any remembering, and no physics left that would permit it. I have thought about why this particular idea travels the way it does, and I think there is something else in it too. Most catastrophes are things that happen to you from outside. A star explodes, a rock falls, a plague spreads. This one is different in kind, because the thing that fails is not an external agent, it is the ground. It is the set of rules that make you a coherent object rather than a collection of unrelated particles, and the claim is that those rules are provisional and that they are sitting in a hollow and that nobody can guarantee the hollow is deep. That is not a threat. That is a revocation of the assumption underneath every other threat. That is not a fear of death. Death is ordinary and everything does it. That is a fear of a thing that is not just an ending, but the removal of the possibility of endings. And I think that is what people are actually reacting to when they say this idea frightens them more than any other. I think they are right to react to it. I just do not think they are reacting to a live threat. But there is something in this subject that does keep me awake, and it is not the bubble at all. It is a coincidence, and nobody can explain it. Take the two numbers that decide everything, the mass of the Higgs boson and the mass of the top quark, and plot one against the other. The plane divides into regions. There is a region where the vacuum is absolutely stable, where the potential never turns over, where there is no deeper minimum anywhere, and no bubble is possible even in principle, and the universe simply is what it is forever. There is a region where the vacuum is unstable, where the potential turns over so early and so violently that the field would have fallen out of its hollow long ago, in the first fractions of a second, and no universe like this one could exist at all. And between them there is a strip, narrow compared to the whole plane, where the vacuum is metastable, where the deeper minimum exists, but the barrier is high enough that the field is still sitting where it started after 13.8 billion years. We are in the strip, and we are not comfortably in the middle of it. We are near the edge, close enough that the boundary with absolute stability sits within about 2 to 3 standard deviations of our measured values. The uncertainty on the top quark mass alone straddles the line. Improve the measurement of one particle's mass by a small amount in one direction, and the conclusion of this entire video flips from metastable to stable. Out of every pair of values the universe could have chosen, out of the whole plane, it picked one that lands on the boundary. That is the thing I cannot let go of, and it has almost nothing to do with doom. Because a boundary is a strange place to find yourself. If the numbers had come out deep in the stable region, nobody would have thought twice about it. If they had come out deep in the metastable region, with a lifetime of 10 to the 10,000th years, it would be a curiosity and nothing more. Instead, they came out perched on the dividing line, in the one place where the answer is genuinely uncertain, and where a small correction in either direction changes the character of the universe. And it is not the only place where our numbers look suspiciously balanced. The mass of the Higgs boson itself is a puzzle of the same kind. In the theory as written, that mass should be dragged up toward the highest energy scale in physics by quantum corrections, and it should be enormous, and it is not. It is 125 giga-electron volts, which is absurdly small compared to where the theory wants to put it, and the cancellation required to keep it there is precise to something like 30 decimal places. That problem has a name, and it has been the central preoccupation of theoretical physics for 40 years, and nobody has solved it. So the same particle whose mass we cannot explain is the particle whose mass, paired with the top quark, puts us on the boundary between a stable universe and an unstable one. Two unexplained coincidences in the same place involving the same field, and that field is also the one that fills empty space and makes matter possible. I do not know what to do with that. I do not think anybody does, but I do not believe it is nothing. There are three ways to read that. The first is that it means nothing. It is a coincidence. We are pattern-seeking animals, and the universe is under no obligation to arrange its constants in a way that seems significant to us. The line is only a line because we drew it. There is nothing physically special about the boundary, and finding ourselves near it is exactly as meaningful as finding ourselves near any other arbitrary place in the plane. The second is that it is a clue about physics we have not found. The standard model is not the final theory, and one of the things a deeper theory would have to explain is why the parameters have the values they have. Some proposals predict that a system with the right kind of dynamics naturally ends up sitting exactly at a critical point, on the boundary between two behaviors, in the same way that many systems in nature tune themselves to criticality without anybody arranging it. If that is what is happening, then this near coincidence is not a coincidence at all. It is a fingerprint, and it is pointing at the thing that comes after the standard model. The third reading is the one about selection. If there are many regions of the universe, or many universes, with different values of these constants, then most of them are in the unstable region, and decayed instantly, and have nobody in them to notice. The ones deep in the stable region are fine, and we, having to exist somewhere the numbers permit us to. On that reading, the boundary is where you would find observers, and the coincidence explains itself, and it is deeply unsatisfying and might still be right. And I want to be honest about the pull of the third reading, the one about selection, because it is the one I find hardest to argue with, and the one I like least. If the constants of nature vary from place to place, then the question of why ours have the values they have gets a very boring answer. They have those values because in the places where they have other values, there is nobody to ask. It is not an explanation in the sense that a physicist wants, because it predicts nothing and forbids nothing. It simply notes that we had to end up somewhere the numbers permit. The trouble is that it might be true. Unsatisfying is not the same as wrong, and the universe is not obliged to give us an explanation we find intellectually rewarding. I do not think it is nothing. I want to be plain that this is my position and not a finding, and that there are very good physicists who take the first reading and think the rest of us are reading tea leaves. But I have looked at that plane and at where we sit on it, and it does not feel accidental to me. It feels like the universe is standing on a line and we do not know why, and the fact that this happens to also mean that our vacuum is technically doomed on a timescale of 10 to the 526 years strikes me as almost a side effect. The doom is the part that gets the headlines. The coincidence is the part that is actually telling us something. And there is a way to find out, which is the part that makes this a live scientific question rather than a philosophical one. The answer depends on the top quark mass, and the top quark mass can be measured better. It requires machines that do not yet exist, colliders designed specifically to produce top quarks in enormous numbers under conditions where the theoretical translation problem I mentioned earlier can be done cleanly. Those machines are being designed now. If they are built, the uncertainty on that mass shrinks by a large factor. And when it does, one of two things happens. Either the point on that plane moves clearly into the metastable region, and the conclusion of this video is confirmed and sharpened, or it moves into the stable region, and it turns out the vacuum is permanent after all, and nothing I have described tonight can ever happen. That is a real experiment with a real answer that could be settled within a few decades. The question of whether reality is permanent is not a matter of opinion. It is a measurement we have not finished making. That is where the honest end of this subject is, not in the bubble, in the fact that the two numbers that decide whether reality is permanent came out sitting on the boundary, and nobody can tell you why, and nobody has a theory that explains it, and the best minds working on it disagree about whether the question is even meaningful. So let me put the last question to you, and then I will tell you what I think it all means. If it turns out that the vacuum is stable, that the top quark mass shifts by a fraction, and the whole shelf we have been standing on turns out to be the bottom of everything after all, does that change anything about how you feel tonight? Or does it only mean that one of the many ways this could end has been struck off a list that remains, in every other respect, exactly as long as it was? I know which way I lean. I am not sure I can defend it. And the emptiest place anyone has ever found, 330 million light years of almost nothing, is full of the field that those two numbers describe. The thing I keep coming back to is not the bubble, it is the number. A 1 followed by 526 zeros, and a universe that is only 13.8 billion years old, which means that on the timescale of the thing we are supposedly afraid of, everything that has ever happened has not yet finished being the first instant. So no, I do not think it is coming. I think the universe has been throwing single particles at itself with the energy of a thrown baseball, in numbers I cannot hold in my head, in every direction, in every corner of everything we can see, for the whole of its existence, and the floor has never once given way. That is not faith. That is the strongest measurement anybody has ever made about the stability of reality, and we are standing inside the result of it. But here is what does keep me awake. Nobody can tell you why the floor is deep enough. Plot the two numbers that decide it, the mass of the Higgs and the mass of the top quark, and we do not land safely in the middle of the safe region. We land on the line. Move one of those masses by a fraction, and the answer flips. Out of every value the universe could have chosen, it chose the edge, and nobody knows why, and nobody has a theory that explains it. So when you look at that void, at the emptiest place anyone has ever found, 330 million light years of almost nothing, understand what you are actually looking at. That emptiness is the only thing holding you together, and it is sitting in a hollow it has no particular reason to be sitting in. And it has held, so far, for 13.8 billion years, but is all safe has ever meant, so far. If you got something out of this, a subscribe keeps these coming, and I would be glad to have you here for the next one. Sleep well.